Hello, this is my connection for the lab number 7 where we're going to measure serial I/O signals. So you can see I have the picoscope connected. Channel A is measuring the transmit data pin, which is the second pin over. And the rs232 signal is on this little header and it's connected to channel B. As you can see here, I've got it connected to channel B. So that's how you want to have the hardware set up. Make sure that your board connection looks like this one. The silver DB9 connector comes out over to this right-hand side opposite to the USB connector. And make sure the pins on the sign line up. For example, the reset, the 3.3 volts, they have to match up the reset and the 3.3 volts on the Omega. If you don't do that, you might damage your board. Also, take a picture of how you had your wires connected when you were working with the robotics system, because we're using it for both robotics and for industrial telecom. Hopefully this helps. All right, this is the Arduino program that I'm running, and it's just a test program that outputs serial data. So in the setup, you have to make sure you use serial.begin. The 9600 refers to the number of data bits per second. And this tells me that I'm transmitting using 8 data bits, no parity, and 1 stop bit. Okay, once I've done all that, in my main loop, I use the command serial.write, and within brackets, I use a 41. 41 happens to be the ASCII code for the letter A. The X here indicates that the number is in hexadecimal, and it's going to be transmitted on the transmit data pin, and then I put a delay of 20 milliseconds. This is just going to make it easier to trigger the scope. So here I have my picoscope display showing me the captured data, and I'm using 2 traces. The first trace is the TTL data. This is the one on the transmit data pin. And you can see I can move this up and down by clicking on that, but make sure it latches on a 0. And this is called my serial decode, and it's decoding this information here. And it's showing me, in this case, the value as the ASCII code for the letter A. And this lighter gray indicates the start bit, which is a logic low, and the stop bit, which is a logic high. So in between that are 8 data bits for the 41. Okay, and it starts off by transmitting the least significant bit first. So that's the 1 in 41. And then there are a bunch of lows, and then a high and a low, and then the stop bit. Now below that in red on channel B is the rs232 data. This is the one that's at a higher voltage so that we can transmit and receive at further distances up to, let's say, 50 feet. Right? And one of the things that you notice over here is the red trace is controlled, the voltage is controlled over here. And I'm just going to put the 0 right at this point here. And I'm going to put some markers. Okay, and I can do that just by dragging them from up at the top. I want to see the high voltage level. It's about plus 7 volts. And the low voltage level, it's about minus 5 volts. And so rs232 signals go above and below 0 volts. And the negative voltage is called the mark, and that's where it idles. And idle means it's not transmitting any data. And the top signal is called the space. If I want to see the width of just 1 bit, what I can do is zoom in. And to zoom in, you just scroll your mouse wheel, and that's what I'm doing here. And then you can see this window. I can move it in to zoom in a little bit more. It makes it easier to measure these times. Okay, so I'm going to measure just the width of 1 single bit, and it should be equal to 1 over 104, or sorry, 1 over 9600 bits per second. So I'm doing that right there. And you can see the width is about 104 microseconds, which makes sense. 1 over 9600 is going to be equal to that value. Okay, and then we could see each of the bits being transmitted. And down below here tells me that the data is 41 in hexadecimal, and the end time, the time it takes for one frame, is 1.043 milliseconds, which makes sense, okay, because we have 10 bits. If I put the cursor at the beginning right here and at the end right here, you'll see that it adds up to 1.04 milliseconds, which is 104 microseconds times the 10 bits. So everything here is making sense. Now, the other thing I want to show you while I have the screen up here is how I've set up my trigger. Okay, so the trigger is over here. I'm in normal mode, so it's just going to trigger and hold. I have to change the type to pulse width. So there's actually a list here, but I want pulse width, and I'm triggering on channel A. My pre-trigger is at 10%. So that just means where it is on the screen. It's the first division. My threshold level is 2 volts. You see that yellow little icon on the screen. The delay is 0, hysteresis is 0, and the pulse direction is positive. That just means that before it triggers, it was sitting at a high level. And I want that high level to be there for more than 10 milliseconds, which I will not get in the data, only during that idle state. Okay, so make sure you have normal, pulse width, channel A, pre-trigger 10, the threshold 2 volts, positive direction, greater than 10 milliseconds. You have to make sure all of those things are set up correctly. And then I'll show you how to set up the UART. So this is something called a serial decoding, and I'm going to click on this. So there's 2 steps here. I want to trigger or decode on channel A. I don't want to invert. My trigger level is going to be 2.4. Hysteresis, not too critical, but let's leave it the same. My data rate is 9,600 bits per second, or 9.6 kilobits. No parity, 1 stop, 8 data bits, and least significant bit is transmitted first. And I move on to the second screen. I want to graph my information in ASCII, and the table to be in hex, and all of these things set to off, and all buffers. And once you've done that, click on finish. Now, the place where you'll find serial decoding, if it's not one of the favorites, is under more, and here's serial decoding. If you want it to appear in this screen, just click on the star, and that makes it a favorite. Okay, so that's what it's going to look like when you're transmitting. And if you want to turn off the zoom, you do that. If you want to zoom, you use your mouse, and then you can move this window back and forth. Okay, but for now, I'm going to turn off the zoom, and I can change the time base to zoom in or out as well. Okay, and I'm setting it to 500 microseconds per division. Now let's try another letter. Let's try lowercase a. I'm just going to stop this. So actually I changed the software so that I'm going to be transmitting the hex code 65. I'm not sure what it is in the ASCII table. I'd have to look it up, but we'll find out when we run our program. The other thing that's important is when you compile the program, make sure the switch on that board is set to the off position. It won't upload properly if it is. The other thing to make sure of while you're on this screen here is go to Tools. Make sure that your board is the Mega 2560. Make sure that your COM port is set properly. In my device manager, you can see here that I have 2 serial port devices, my Mega connected to COM5, and I actually have a device called a USB to serial. Very, very useful device if you work in the electrical electronics trade. You can buy these on Amazon for about $25, but very, very useful to have. So I'm going to close this off. I'm going to download my program, as I said, with that switch in the off position. And I've done that now. And remember that it's 60. So here I'm running my program, but you see that there's no rs232 signal because my switch is in the off position. So I put it back in the on position, and now it's transmitting the data. You can see the shape is different, okay, because it's the value 65. And 65, if I break it down into binary, if I break 65 hex down into binary, it's equal to 01100101. And it's transmitting least significant bit first. So it's going to be backwards. And backwards would be, this is my start bit. And here I have a 1, 0, a 1, 2 zeros, 2 ones, and a 0. That's a 65. Okay, and then I have my stop bit. And down here it tells me that the data is 65 as well. Here I'm going to change my program so that I have even parity. So I have to download that. I have to move my switch, download it. Sorry, upload. I'm used to the PLCs. So this is uploading. And now I switch back to now you see that I seem to have an error here, and I think that's because my software is not set up correctly. So let's make a change. So I think I have to go into my serial decoding, and I have parity set to none, but I'm actually transmitting with even. Okay, so click on next, all of that's okay, and now I don't have any errors. And what parity will do is actually check to see if the number of high data bits that we have here totals to an even number. If it does, it makes this equal to 0. If it's an odd number, it will make the parity bit equal to 1 so that it completes the check. And it's showing you that it's done a parity check. You can see down here the parity bit is 0, the check is okay. If there was an issue, the check would fail. Okay, and you could retransmit the data. Let's try using a different number. And we're going to change to, I'm changing to hex 66. I'll download that. Okay. Well, this didn't work out the way I thought, because actually the F has 66 would also have 2. So we need a 67. So let's switch it to 67, because you can see there's a high here, and 2 highs. That gives you a total of 4. So the parity bit's going to be 0. So 67 should do it, because there's going to be 2 highs from the 6 and 3 highs from the 7. That's 5. And we have even parity. So let's download this, move my switch so I don't get a download issue. Good. Back to the other position, back to my software. Okay, this makes more sense now, because we have, and our parity check is okay, and our parity bit is a 1, because we have 1, 2, 3 highs, another 2 highs, that's 5, but we have even parity, so we want to make sure that this bit is equal to a 1, so it adds a 1 here. And on the rs232 side, it's going to be the opposite to that. Okay. Now, another program that we can use is called Putty. So you can see this Putty program here, and if I want to operate it with serial I/O, I select serial, and I have to get the right port, and I can double check that. So my serial port should be 7, and I'm going to click on 7, and then open up the serial monitor. And what it's doing is displaying the letter G continuously. So this is actually going to my computer, and it could go to any other device. So whatever I happen to have that set to, it'll display that message on that serial port software. Hopefully this helps.